All right, here we go. Inverse variation. Excuse me, we talked about direct variation in our last lesson. All right, direct and inverse variation are related, very much related. Okay, but before we talk about how they are related, let's just start with our Explorer for today. Okay, our Explorer for today says assume two cities are 72 miles apart and you'll be driving from one to the other. We write the distance form, the formula distance equals rate times time, so that the formula, so there's a formula for time. Okay, use your result to write an equation in which time is a function of rate, given that the distance is always 72 miles. Well, if I have distance equals rate times time, and I want to solve for t, I want to get t by itself. The only thing, excuse me, stopping me from that is the r. So I would divide both sides by r and say t equals d over r. Now it says use your result to write a function, all right, given that the distance is always 72 miles. So t equals 72 divided by the rate. Boom. There's our answer for part A. So it says use the equation in part A to complete this table by determining the value for the time by determining the time of the trip in hours and minutes if the average speed varies. Round your answer to the nearest hundredth when necessary. All right. So first thing I want to do, define the time. Okay, it's t equals 72 divided by the rate. All right, so I'll do the first one with you. It'll be 72 divided by 40, and you will put that here. Then to get the time in minutes, I would just multiply this by 60. So times 60 and get 100. All right, so I want you to complete this table. Go ahead and go down and complete the table. Do 72 divided by 50, 72 divided by 60, 70, and so on and so on. All right, so here are my numbers here. Okay, we want to decide if the relationship between time and speed is linear. No, it's not. Because it's not consistent. What do I mean by consistent? Well, our miles per hour is consistent, but our time is not consistent. There's not a constant rate of change. Each line on the table, find the product of the speed and the time. What do you notice about the product? Well, if I multiply 40 times 1.8, let me get my handy dandy calculator out. 40 times 1.8, oh, I get 72. If I do 50 times 1.44, oh, I get 72. All right, so what happens? Always 72, and then I guess it'll be miles. That makes sense, right? That makes sense because, well, the 72 was in our original problem. When one of the quantities of the table when one of the quantities in the table increases, the other decreases in a particular way. Specifically, whenever speed doubles, okay, so I go from 40 to 80, that's doubling my speed. What happens with the time? I go from 1.8 to 0.9 or 18 to 9. Well, what happens? Time is cut in half. And that would go in that blank. I just don't have a big enough blank to write it. So our time is cut in half. Okay, which makes sense because our speed is doubled. All right, so our time should be cut in half. Okay, use the data to graph a time versus the speed. All right, so take a second and graph the time versus the speed. I want you to graph the hours and not minutes. Okay, since it says miles per hour and it says hours up here. All right, so go ahead, take a second and do that. This is a rough sketch of my graph. Okay. F says there is no speed you can drive that will result in 0 hours for the 72 mile, which makes sense. Okay, then you wouldn't be driving. How can you see this in the general shape of the graph? Well, what was it? It says you never. in a time of 0 hours for 70 mile drive. Well, this is the speed, right? Okay. Our speed, if I had hit 0 hours, our graph would cross this axis right here, x-axis. So you can see the graph never, the line. Your speed gets slower and slower. The time needed to travel 72 miles gets longer and longer. However, your speed can never be 0, or you wouldn't be moving. How can you see the general shape of the graph? The line gets close to the vertical y-axis, but never. If I were to continue this line, it would very closely approach, continue to approach this vertical line, but never cross it, because you can't have a speed of 0, which we all know, which makes sense, which would make total sense to me. Let's keep going. So what are we gonna talk about today? Today is, like I said at the beginning, can you recognize inverse variation? Can you write a variation model for each type of variation? Because we're going to discuss well, and do you know how to solve variation problems by writing your own model? All right. So direct variation, if you remember, was y equals k times x. Well, this one is going to be y equals k over x. Okay. That's inverse. Inverse meaning, well, it's the inverse. Inverse of x is 1 over x. Inverse functions. Varies inversely or indirectly with the other. The constant, we talk about that constant, which is k, etc. So, for example, if a commute is 60 miles, yada, yada, yada. All right. So this is what the graph of our inverse variation is going to look like. Okay. These are the two options here. If my multiplier is greater than 0, it'll look like this. If it's less than 0, meaning if it's positive, it'll be here. If it's negative, it'll be so the general appearance of the graph is not sufficient, yada, yada, yada. Okay. Using the table of the values in the table, verify that y varies inversely with x by showing that the product of x and y is constant. So in direct variation, we did y divided by x to see if it was direct variation. Here we're going to do x times y. So if I do x times y, I get 240, I get 240, I get 240, and guess what I get? Oh, I get 240. That tells me that our multiplier, our k value, equals 240. All right, that's how you find your k value. Okay, so y does vary inversely with x. If k is 240, then I would write my equation like this. Now, if I was like, wait, that doesn't look like what we did here, that's true. But if you were to, get the 240 by itself, what would I do? I'd multiply by x, and I'd have x, y equals 240. That's where this 240 comes from. That's really how you find your multiplier, but that's not what we're doing. Okay? That's where this work comes from. All right, so our answer, our equation for this problem is this. Okay. So then the book gives us an example. Suppose y varies directly with x, or excuse me, indirectly when y is 100, x equals 2. Okay, so if you look here, y equals k over x, well, y is 100 and x is 2. Multiply both sides by 2, I get k equals 200. Let's use this to find y when x is 8. I just do 200 divided by 8. Those are the types of problems you can see in your homework. All right, for sure. Okay, so let's look at number 3. Suppose m varies indirectly with z, and m is 30 when z is 2. Find m when z equals 6. Solve using an inverse variation model. State the value of k and write the variation model as your solution. So M varies indirectly with Z. That tells me that, M equals K over Z. When M is 30, K is 2. So 30, Z is 2, equals K over 2, multiplied by 2, multiplied by 2, 60 is my K value. Okay? So now it says what? Find M when Z is 6. Well, when Z is 6, my equation is this: y equals 60 over Z. So find M when Z is 6, M equals 60 over 6. So M equals 10. The second part says solve using one equation. That would be really long. That'd be using the proportions. We didn't really do that. So I don't want to do that here. So we're going to skip part B. All right, we're going to skip part B. All right, we're just going to stick to this way. So we have two different types of variation that we've talked about. Two main types, direct and inverse. We'll discuss the difference between the two in a minute. This is how it works. Again, we're going to stick with option one. We'll stick with. Okay, that'll be the option that we refer to. All right, we're going to ignore option 2. Okay. So a company manufactures plastic storage containers. The cost per container varies inversely with the number of containers manufactured. If the cost is $125 per container when 4,000 containers are made, what's the price when 5,500 are made? The cost varies inversely with, I'm going to use the N for containers like that. So if our cost is $1.25 and the number of containers is 4,000, okay, that's how I would find our K value. So if I do that, I would end up multiplying both sides by 4,000. Answer K equals 5,000. So now it says, all right, what is the price, so our costs, when 5,500 containers? I'm going to do 5,000 divided by 5,500, and I get 0.909. So that's 0.91. How about that? Good for us. Good job. Thank you so much. When a variation equation involves more than two variables, it represents compound variation, which we kind of talked about in our last video. Joint variation, which was introduced in section 4.7, is compound direct variation. Okay, that just means there's compound direct variation means like y equals k x z, more than one variable. All right, more than one. That's what they're talking about. So the formula F equals G, M1, M2 over R squared calculates, so in this case, G would be our multiplier, calculates the force between two objects with masses M1 and M2 in kilograms where they are R meters apart. G is our gravitational constant. Think that's our K value. All right. Think about the force between two magnets as you answer the following questions. Okay. If the distance between the two magnets increases, okay, if the distance between the two magnets increases, what happens to the force between them? Well, that would decrease. Think about as two objects, if I have my two, as these are being pulled apart, the force between them, so it's like the space between them, like what's pulling them together would decrease. The amount of pull towards each other would decrease. So if the masses of two magnets increase, what happens to the force between them. So as these magnets get bigger and bigger and bigger, what usually happens, bigger magnets become pulled together more. The constant of variation, which we found out at the beginning, was G, right? It says here, the constant. Force varies blank with mass and blank with distance. So if you look here, the mass is our M1 and M2, so that is direct variation. Directly. And R squared is in our numerator, so that's inversely. Okay. I should have, when I was talking about part A, distance in this particular situation is R. As distance increases, so as R increases, I'm dividing by a bigger and bigger number. If I divide by a really big number, my number is going to be a lot smaller. Okay, and we're going to pause there and talk about the other types of variation in class.